This is another video in this series for Math 1133 for UTSA. Uh, Again, we have a bit of a format change from prior videos. So basically, I have edited together some videos I made back in April covering related rates, which is an application of implicit differentiation. I was able in the previous video to clean up the audio pretty well, so the background noise was very minimal. Same case in this situation. So there are 5 more examples, so let's get to it. In this video, we'll discuss the concept of related rates. So in previous videos, we talked about implicit differentiation, where you can find the derivative of an expression involving one variable, but with respect to a different variable. So as a just quick example, if we have an expression like y squared, right? And I want the derivative with respect to x. Well, this sort of implies that those variables are connected. Like if y and x are totally connected, then the rate of change would be, say, 0, basically, because this is saying when the x variable is changing, how does this expression change? Well, if they're unrelated, then this would be 0 in that case, because they're not connected. Changing x doesn't affect y, so 0. So when we ask this and it's assumed to be meaningful, well, that means that they are connected, that y equals some function of x. We just don't know what it is, okay? So basically, when we have y squared as the input for this derivative operation, we have a function of a function. This is g of x squared, right? Y squared equals g of x in parentheses squared. We have an inside function and we have an outside function. So we need to use the chain rule, right? So if you were to apply the chain rule to this, looking at that, you'd say, oh, well, my outside function is 2. So dx of y squared, or rather I should say it's 2 times something. This is dx of g of x squared, right? So this is going to be 2 times the inside function times the derivative with respect to x of that inside function. Okay, because we have the power rule and then the chain rule. Okay, power rule and chain rule are both at work. Okay, well, the inside function will just sit here, 2 times g of x, and the inside function will sit here, derivative of g of x. Okay, now 2 times g of x, well, g of x is y, remember? So this is just 2 times y. Times, well, since we don't know a formula for g of x, we're just using it symbolically, it's what y is, well, this is dy dx, whatever that derivative might be. We don't have access to it right now because I don't have a formula for g of x. So this is what's going on under the hood. When I look at this guy, I go, oh, the outside function is the exponent 2. I'm squaring something. So the derivative is going to be 2 times the inside function, and then times the derivative of that inside function, okay? Now, that's just a survey of implicit differentiation. Now, how does this relate to related rates? In related rates, instead of having derivatives with respect to x, we're going to have derivatives with respect to t, time. So like if I had a little display error there, I wonder how that happened. Oh well, let's not worry about it. If I have something like dt of y squared, y is changing over time, well, this is the same idea. This is 2y times dy dt. Whatever that happens to be, that's what it is. Until I have access to that as a formula or as a number, I just have to leave it the way it is. In a related rates problem, typically you'll be given, well, y is changing at this rate, 2 units per second or 2 units per day or whatever it is. Now, let's say I had an equation that described something tangible. So I'm going to use something that's, let me get another page here. I'm going to use something that's, current events, something that's relevant now. Let's say that the number of employees, let's say at HEB, right, who are going to get sick from customers being sick. Someone with coronavirus, goes to this, they don't know they have it yet, right? They're asymptomatic. They go in to buy some toilet paper, right? They're hoping to get some. and they, ask an employee, hey, are you guys restocking today or tomorrow morning? And then they buy something else because there's no toilet paper. They buy some, I don't know, ramen or something, and they go and they pay for it, right? And assuming that we don't have these social distancing practices in place, which are useful, they're having an effect. But supposing we didn't, right? This is like a month ago or 2 months ago. There's no, say 2 months. There's no social distancing. Someone who has this virus, they don't know they have it. Well, let's say the number of employees, let's say across all HEBs, or it could even be one large HEB. Pick like the one Days of Olive, right? So let's say the number of employees who become sick at that store as a result of just the general public coming in, whoever it might be. Let's say that it's something like, I don't know, 0.1% of the number of customers squared. Okay. Let's say there's 2 points of contact. The customer comes in, they ask an employee a question, and then of course when they go to check out, they have to interact with the cashier. So there's 2 points of contact. I'm not an epidemiologist. Let's just pretend this makes sense. I'm just making up an example, right? So let's say the number of employees who get ill, who become ill, let's say that is in proportion to the square of the number of customers that day. So number of customers each day, right? And let's say become ill each day. This is both like per day, right? Well, what I can say is, well, what would happen if fewer people go to HEB? Let's say on a day-to-day basis, fewer of them are going. So let's say at this particular store, there's, let's say, I don't know, 5,000 customers per day. And that's probably not even a big HEB. That's probably a little HEB. Well, if the number of customers is 5,000, then the number of employees who become sick at some point, after interacting with that person, maybe this number is too large, maybe it's exaggerated. Let's add a couple more zeros in there. Let's say 0.000, let's say 0.1. Let's do like that, right? An extra zero or 2 extra zeros. So then E is going to be, for that particular day, 0.00001 times 5,000 squared, right? That's 5 million times that's going to be 50, okay? Oops, sorry, struggling with the interface here. I hit the wrong button. 50. So that day, 50, and this doesn't have to be coronavirus. This could be anything. And again, I'm making this up, so don't take the numbers too seriously. So 50 employees will become ill from having worked that day, right? Based on having 5,000 customers that day. Well, what if the number of customers goes down by, let's say, 1,000 from one day to the next? C goes down. Let's say 100, by 100 customers, by 100 each day. Okay. Well, that can be represented as dc dt, the rate of change with respect to time, the derivative of the number of customers as a function of time. That's going to be negative 100. It's going down by 100 each day, and we'll say that t is in days. Okay, well, if that happens, how will that affect the number of employees who become ill each day? Well, we can use implicit differentiation to find that. What I really want to do is take this equation that relates the number of employees who become ill to the number of customers who are seen that day, and I want you to turn that into an equation about the rate of change, the rate of change, or the rate at which employees become ill and the rate at which customers are coming to the store, right? Again, assuming no safety measures. So I'm going to apply what I like to call a time derivative to this equation. So I'm going to copy the equation down here. Okay, so E equals 0.00001 c squared. I'm going to apply the derivative with respect to time to both sides. Okay, so on the left, I'm finding, well, what is the derivative? What is the rate of change in the number of employees who become ill with respect to time? Well, that's dE dt. the number of employees who become ill as a function of time is some formula. I don't know what it is. I don't have a formula for it. So I'll represent this as dE dt. Okay. And the same thing on the right. This is slightly more complicated. I have to apply the derivative as a function of time to 0.00001 c squared. So I'm going to use the power rule and the chain rule. So this will be, come on, struggling with the interface again. This will be the power rule 0.00002, right? The 2 multiplies against the 1. C to the first power times, using the chain rule, the derivative of the inside function, which is c. Again, I don't have a formula for c as a function of time, but it's implied to be one. dc dt. Okay, so if dc dt is negative 100, as I said, and c is 5,000, how will that affect the number of employees who become ill? Well, then if dc dt, there's other notation for this, but we'll get to that in a later video. We don't need to get bogged down with notation. If dc dt is negative 100, then dE dt, well, that will be 0.00002 times, C was 5,000 for that particular day, times the rate of change for that day. So the next day will be 4,900 customers instead. If we multiply this together, we're going to get, I believe, 10, I think. Do I have a calculator handy just to be sure? I think I do. Here we go. So let me turn the light on. Sorry about that. Okay, so 0.00002 times 5,000 times negative 100, and I get negative 10. Of course, negative. What that represents is the following day, 10 fewer sick employees. So if you just reduce the number of customers coming in by just 100, from 5,000 down to 4,900, you'll go from 50 employees who become ill down to 40, down by 10. So this is what related rates will do for you. When you have an equation that connects two quantities, number of customers, number of employees, that kind of thing, and you know how one or the other of them behaves over time, you can then decide, well, how does the other one behave over time by finding the derivative with respect to time on both sides of the equation and plugging in the numbers that you know. So this is a relatively basic example, and hopefully you can see the importance of this kind of analysis, calculating these kinds of things. So in the next few videos, we'll do more examples like this, but a little bit more complicated as far as the calculus component. In this video, we will do a classic example of a related rates problem using basically a ladder leaning against a wall. That's the classic example. So I'm going to start by drawing a diagram. There we go. And I need to clean this up a little bit. So, oops, not there. Here. Let's say we have a wall and a floor. Okay. And then we have a ladder leaning against the wall. Okay. And let's say that previously the ladder was like this, like leaning up real close, right? You know what? Actually, I'm sorry. There we go, much better. So originally the ladder was like leaning up against the wall, right? And then the bottom was being pulled out. So let's say we have a 10-foot ladder, okay? And the bottom is being pulled, let's say at a rate, let's say, I don't know, 2 feet per minute. So pretty slowly. Well, let's say per second, 2 feet per second. So pretty quick, okay? It's essentially falling down by someone pulling at the bottom. Now, the bottom doesn't go faster as it moves, just from start to finish, from fully parallel with the wall to fully parallel with the floor. That whole transition, the bottom of the ladder, the base of the ladder is moving at a constant rate of 2 feet per second. Okay. Now, the classic question then is, of course, the bottom is moving down, right? It's going to end up on the floor at the end. At what rate? at what rate is the top of the ladder moving? Because it's not 2 feet per second. And if you go and you probably don't use a ladder to do this, that'd be, risk damaging something. But if you got a yardstick, if you have a broom, if you have anything like that, you can go lay it against the wall and pull the bottom out. If you watch the top initially drops quickly and then slowly at the end. So the top does not move at a constant rate, which maybe is surprising, maybe not. But then the question is, well, at what rate? So that's the statement of the problem, and this problem is typically you're not given an equation to deal with. Now, in this course, on the online homework and the exams, you'll be given an equation. Don't worry too much. So for this one, I'm just going to tell you, without going into maybe all the reasons why, maybe once I explain it, it will be pretty clear. I need to use the Pythagorean Theorem because I have a triangle here, right? I'm going to call the base of the triangle x and the altitude of the triangle y, just for convenience, x and y. And then the hypotenuse of the triangle is the 10 feet that the ladder is made up of, right? So I can say that x, y, and 10 are related by x squared plus y squared equals 10 squared, right? Pythagorean Theorem. In a sort of a calculus course for scientists and engineers, they would be expected to figure that out. You should know that already, right? You should know how to try to approach this kind of problem. But for this class, you're not engineering students, so we'll make things a little bit easier in the sense that you're generally given the equation to start with. Okay, so what I need to figure out, I have this equation. What I need to figure out is how to interpret these numbers. Which of these change over time, and which of them do not change over time? If you think about it, we hope that the length of the ladder does not change over time, right? You're not going to start cutting pieces off of it. And I've already told you that this number does not change over time, the 2 feet per second. But it may be pretty obvious that the x does change as a function of time, okay? And the y does change over time. And I actually left out a piece of information. We need to ask, at what rate is this moving at a certain point in time? I need to specify when, because it changes over time. It's not constant, as I said earlier. So when, let's say when x equals 4, when the base of the ladder is 4 feet from the wall, how quickly is the top of the ladder moving? Okay. Now, in the previous example, we knew we were doing related rates, so we applied a time derivative to both sides of the equation. So that's what I'll do here. I'll say that I want to find d dt of both sides of the equation. There are several steps in this kind of problem, and for some of the steps, the order is optional, which order you want to do things in. So there's actually something we haven't done yet that we could have done already, but that's fine. We don't need to necessarily do things in the most efficient order every time. I think it's important just to see the overall process of how do you solve this problem. So now, when I find the derivative with respect to time of x squared, remember x is not the variable with respect to which the derivative is being applied. The derivative is being applied with respect to t, not x. So in previous examples on implicit differentiation, we would find the derivative with respect to x of like y squared, for example. We'd have to use the chain rule because x and y are different variables. That's the situation we have here. We're not using x as the variable for the derivative. So I have to apply the chain rule. So the derivative of x squared, I'll use the power rule, so 2x. But then I have to use the chain rule, dx dt plus, and again, I use the chain rule here when I find the derivative of y squared with respect to time. So this will be 2y times dy dt equals, and this might be obvious, but perhaps not. The derivative of a number is always 0, regardless of the variable. 100 does not change when time changes, so this is 0. Okay. So this is an equation that relates not just the base and height of that triangle, or base and altitude of that triangle, but also the rates at which they are changing. Now, we were given one of the rates, so pause the video and think for a second. Which rate is this 2 feet per second? Is it dx dt or dy dt? So maybe you've thought about it. This is dx dt. This is the rate at which the bottom is being moved or being pulled. So this is the rate at which x, being the distance from the base to the wall, changes. So I can say, in this part I could have done earlier, I could have said, okay, well, dx dt, that is equal to 2, okay? Because this this length here, this distance is growing by 2 feet per second. The base is being pulled away from the wall. So that means this number can plug in there, okay? And this 4, when x is 4, that plugs in there. Now, ultimately, we are looking for dy dt. What is the rate at which the top is moving? Which is another thing we could have said earlier. So I can say, well, this is not really a question mark. I know that this is dy dt, and I just need to determine what number that is. So I've got a number for x. I've got a number for dx dt. I do not have a number for y. I need to find out a number for y. And that might not be very hard. You might be pretty clear to you, how do I get a number for y if I have a number for x? And so here's the important part. This important point at which to observe something. I should not plug in 4 too early. Before I apply the derivative, x is a variable that changes over time. So I need to find the derivative, and then later I can plug in 4. So here I can plug in 4 for x right here if I want. I should not plug in x too early, because then, well, the derivative of 16 is 0, and I won't get anywhere, okay? So you need to make sure to only plug in numbers for things that do not change, like this 10. 10 squared, I went ahead and put at the beginning, because the ladder length doesn't change. But for both x and y, I can't put in those numbers yet. So how am I going to get a number for y? Well, again, I need to use Pythagorean Theorem because I have a right triangle here. So x squared plus y squared is 10 squared. When x is 4, that will allow me to get a number for y. So 4 squared plus y squared equals 10 squared. So 16 plus y squared equals 100. Trying not to let my y's look like 4s. This one kind of does, but hopefully in context we're okay. So y squared equals 84. So y, now y is always going to be positive, right? Because y is the altitude of that triangle. It can't be negative. So I don't have to worry about plus or minus here. This is the square root of 84. And if you want, that reduces 2 root 21, if you want to simplify it a little bit. Okay, so that's my y value. So now I can take this equation and bring it down here where I have more room. 2x times dx, dx dt, plus 2y times dy dt equals 0. So now I can plug in 4 for x, negative 2, positive 2, for dx dt, right? This is positive 2, plus 2 times 2 root 21 times dy dt equals 0. So I've plugged in all the numbers, either that I was given or that I worked out using the Pythagorean Theorem. So now I can solve for dy dt. The hard part is done, the calculus part is over. I'm just solving an equation now. So I'll subtract 16 on both sides. So 4 root 21, that 4 comes from combining the 2's to make 4, times dy dt equals negative 16. You might notice a way to be perhaps a little more efficient here. So if you do, that's awesome. I'm not worried about being as efficient as possible. Try to make this as clear as possible. So next I'll divide by 4 times root 21. So this will become dy dt equals negative 16 over 4 times root 21. And of course, 16 and 4 reduce, so dy dt is negative 4 over root 21. And this is in feet per second, right? Okay. This is another reason to use the Leibniz fractional notation, because the top will tell you, basically the derivative notation tells you what units to use. The dy is the change in y. Well, y is measured in feet. The dt, well, that's measured, that's a change in time, and time is measured in seconds, so feet per second. Sometimes we'll want a decimal approximation, so let's go ahead and do that for this one. You don't always need that, but let's go ahead and do it for this one just so we can get a more tangible number, because if you look at this, you might be unclear. Yeah, but how much is that? Is that a lot? So this is about negative 0.87 feet per second. Oops. 7 in feet per second. Okay? So not very quick. The bottom is being pulled at 2 feet per second, and at such a time when the bottom is currently 4 feet from the wall, so 2 seconds later, right, the top will be moving at almost 1 foot per second, but not quite. So anyway, that's that example. It's several steps, but that's the classic example of a related rates problem. So in this video, we'll do another example of a related rates problem. Let's say that the equation 10n plus 31p equals 3,500 relates the profit in millions of US dollars to the number of employees for some large business. And let's say that the profit is increasing at a rate of 500 million US dollars per year. At what rate is the number of employees changing? Okay, so this 500 million, this tells me this is the rate of change in the profits. This tells me that dp dt equals 500. The profit is increasing at a rate of 500 year over year, okay? At least for that year. It could be different for the following year. So in order to determine, well, at what rate is the number of employees changing, I need to apply ddt to both sides of this equation. I have an equation that relates the number of employees and the number of employees and the amount of profit. If I find the derivative with respect to time, then I'll find an equation that relates the change in the number of employees with the change in the amount of profit. Okay, so I'm going to find d dt of 10n plus 31p, and that's equal to ddt, of 3,500. On the right-hand side, this is easy because the derivative of a number is always 0. The left-hand side, when I find the derivative of 10n, I get 10, right? That's just using the constant multiplier rule and then the power rule. But the derivative, the variable with respect to which the derivative is being taken is not n, it's t, so I have to use the chain rule. So this is actually 10 times dn dt. Okay. Similarly, in the next term, 31p, the derivative with respect to time will be 31 times dp dt. And then, of course, this equals 0, right? So now that I've found my time derivative, I can then plug in the 500 that I was given as the rate of change for profit. So 10 times dn dt plus 31 times 500 equals 0. And now I can solve for dn dt. I'm going to go ahead and subtract the 31 times 500 from both sides. And I believe that's 15,500. So 10 times dn dt equals negative 15,500. And then I can divide by 10 on both sides. So dn dt equals negative 1550. What this tells me is that when the revenue is increasing, or not revenue, sorry, profit is increasing at a rate of 500 million per year, that correlates with a decrease in the number of employees at a rate of 1,550 employees per year. And that could be something where, to be more efficient, the company can, decrease the number of employees. They don't have to pay them. That can increase their overall profit, their net profit. Okay, in this video, we'll do another example of a related rates problem. So let's say that 2,000 r squared equals n cubed relates the number of employees for a business with the revenue. So this would be, n is in terms of thousands of employees, and r is in terms of billions of revenue, billions of dollars in revenue. So let's say at some point in time, there are 180,000 employees, and there is 54 billion US dollars in revenue. Okay, for the company, I suppose for that year, right? Now let's assume that the revenue is increasing at, let's say, a rate of 7 billion per year. Let's say 7 billion per year, US dollars per year. Okay. And the question is, at what rate is the number of employees changing? Well, we need to interpret these numbers given that these variables are in terms of multiples of employees and multiples of dollars, not just, n equals 5 is not 5 employees, it's 5,000. So here, where I have 180,000 employees, if n is in thousands, that means that n is 180 in that case. If I don't handle these numbers correctly, I won't get the right result. The 54 billion, well, since R is in terms of billions of dollars, that means that R is 54. Okay. Now this last one is maybe the harder one. What is it that is 7 billion? Well, this is revenue increasing $7 billion per year. So something is 7, right? If you think about it, maybe pause the video and think about it. This is the rate of change in the revenue as a function of time. So this is dr dt. dr, make it a little bit neater, dr dt equals 7, okay? So now if I want to know the rate of change in the number of employees, from year to year, how is that number going to change? I can use this original equation. I can find the derivative with respect to time of this equation, plug in the numbers I'm given, and then I can find out here's the rate of change in the number of employees. So let's do that. I'll just copy the equation down here. So 2,000 r squared equals n cubed. Okay, so when I apply the derivative to both sides, d dt, on both sides, then this is a lot like ones we've done already. This is not super difficult. We just have to remember that we are using the chain rule. The variable with respect to which the derivative is being taken is not the same as the variable in the equation, or variables, I should say, in the equation. So I have to use the chain rule for every derivative. I'm not just using the power rule here. So using the power rule, I'm going to have 4,000 times r to the first power, that's the power rule, times dr dt. It's the chain rule. Okay. Change colors real quick. Power rule, chain rule. Okay. And you're always going to be considering the chain rule. You might not always be doing the power rule. Just in this case, we are, because we have r squared and n cubed. We're using the power rule. But for this kind of problem, you're always going to be using the chain rule. Okay, so the right-hand side will be done similarly. When I apply the power rule, 3n squared, that's the derivative of the outside function, then times dn dt, that's the derivative of the inside function. Okay? And now I have an equation that relates r, dr dt, n, and dn dt. Now I have numbers for 3 of these. N, r, and dr dt, I have numbers, so I can plug those in now. If I had plugged in 180 and 54 at the beginning, I wouldn't get a result this way. I mean, I would get, what would that be? I don't know what n cubed is, but I would have some number equals some other number. The two sides would be equal, and I wouldn't really be able to do calculus with that. I have to plug in my numbers after I apply the derivative. Okay, so n is 180, r is 54. So r is 54, so 4,000. It's 54. dr dt is 7. And n is 180. Okay. And dn dt, that is what we're looking for, the rate of change in the number of employees as a function of time. So now I can divide both sides by 3 times 180 squared. So I'll have 4,000, and we're probably going to use a calculator at some point, times 7 over 3. And I'm going to write the 180 squared a little bit differently. I'm going to write it as 180 times 180. Okay, that equals dn dt. You'll see why in a second, why I'm doing that. Now, we are going to use a calculator, but if I see any ways to simplify things, I can do that first. So I notice this 0 and this 0 can cancel, this 0 and this 0 can cancel. And I notice that 3 times 18 is 54. So 3 times 18 and 54 can cancel. So I've got a little bit less to type in. This 40 and this 18 can reduce. So I get, what is that, 140 over 9? I think that's right. Simplify that a little bit, and then we can throw that in a calculator and get a decimal number. So 140 divided by 9, I get 15.555 repeating. Let's round to, say, 3 places. So 15.556, okay? Remember, this is the number of employees in thousands. So that means the conclusion we draw is 15,556 more employees. It goes up because the value is positive. More employees, say either that year or the following year. Oh, that is not how you spell employees. Either that year or the following year, depending on the way the question is phrased. Yeah, so basically we take the information we're given, we make sure to interpret these numbers, we take the scale of the problem into consideration. Employees is in thousands, revenue is in billions. That's very important. Then we apply the derivative with respect to time to both sides of the equation. Okay? Then we plug in the numbers we're given, and then we work out what the result is. And we might need to interpret, well, is this more employees or less employees? That's something we might have to figure out as well. In this video, we'll do another example of a related rates problem. So let's say that the equation 2x squared plus 5xp plus 50p squared plus, equals 80,000 relates the demand for a certain widget, whatever that might be, in correlation with the price for that widget. So let's say that P is the price in US dollars. And let's say that X is the quantity demanded. Let's say, I don't think this needs to be in thousands. I think we'll just go with quantity demanded. Let's say this is like per month. Right? On a monthly basis, this is how many are demanded. So when the price is 30, so $30, if the price is changing on a month-to-month basis, maybe this is a commodity, not a widget, right? Maybe this is, oil or electricity or water or something like that. Let's say that this is going up $2 per month. Okay, so the price is 30, but on a month-to-month basis, it's going up by 2 every month. So $32, $34, $36 as an example. So the question is, how is the demand changing? Oops. Okay. Now, of course, if the price goes up, you would expect demand to go down. Well, okay, sure, but how much? It goes down by how much? So I'm going to need to apply the time derivative to this equation. So dt of 2x squared plus 5xp plus 50p squared equals d dt of 80,000. Okay, so the right hand side is easy. The derivative of a number is just 0. The left side, however, has 3 terms, so we have to be careful to handle them each correctly. The first term is just the power rule, chain rule, nothing too difficult. And the last term, same thing, power rule, chain rule, nothing too difficult. It's like the ones we've done in previous videos. The middle term, however, is a little bit harder because if you don't pay attention, you might overlook this. We have to use the product rule here. We have a product of 2 functions of time. The demand x changes as a function of time, and the price p changes as a function of time. So I'm going to have to use the product rule. So I'll go ahead and find the derivative here. This one, this is 4x dx dt. And the next term I'll put in parentheses. I don't need them, but well, you know what? Let's put the 5 outside parentheses. 5 times the derivative of x times p. And again, I have to use the product rule. So remember that the derivative of uv is u prime v plus uv prime. So in other words, the derivative of the first factor times the second factor plus the first factor times the derivative of the second factor. So I'm going to write this out like this. d dt of x times p plus x times d dt of p. So that's the second term. Okay. I'm running out of room here, so I'm going to move this over a bit. Yeah, that should be okay. Plus, I have to change, go back to this term, not change, sorry, about to say change back to something, but no. I need to apply the power rule to this guy. So 100p times dp dt. And this all equals 0, because of course the derivative of 80,000 is 0. So I still have to work with these guys. It's difficult, I just wanted to do it in 2 steps. So the derivative with respect to time of x is dx dt. Again, we don't have, as before, we don't have x as a function of time, we just know that it changes as a function of time. And then d dt of p is dp dt. Okay, so I'm going to have 4x times dx dt plus 5 times dx dt times p plus 5 times x times dp dt plus 100p times dp dt. Okay. So the calculus part is basically done. Well, yeah, basically the calculus part is done. We're going to have to keep calculus concepts in mind, but we're done finding derivatives. So what I need to do is I need to plug in numbers for x, dx dt, p, dp dt, all of these, well, except for one, right? I'm asked to find how is demand changing. That's dx dt. So I'm not given dx dt. So it's actually only x, p, and dp dt that I'm plugging in. dx dt is what I'm solving for. So I'll make a note of that up here, which we could have if we'd wanted to do it up here. Dx dt equals question mark. That is what we're looking for. Okay. Now, I don't have a number for x. I wasn't given a number for x, right? I was given a number for p, and I was given a number for dp dt, but I was not given an x value. So we have to find an x value. So go ahead and pause the video and think for a minute. How are we going to do that? Okay, so to find x, what I have to do is go back to the original equation. I have to plug in 30 for p and then solve for x to get a number for x, okay? So let me use a different color so it stands out and this doesn't run together. So 2x squared plus 5xp. Now p is 30, right? So 150x after I plug in 30. Plus 50 times p squared. P squared is 900 times 50 is 45,000. So our numbers are getting kind of large, but it's going to be okay. Equals 80,000, right? Yeah, 80,000. Okay, so I'm going to I could divide, but I'll start by subtracting 80,000 on both sides. So 2x squared plus 150x minus 35,000. And the numbers are large, but don't worry. Now, since everything is even, all those coefficients are even, I'm going to divide by 2 on both sides. So x squared plus 75x minus, what is that? 17.5. Okay. Now, it probably is not obvious at all how this factors, but it does factor in a relatively easy way. You might notice this 75 here. That's your clue basically. So I think I did this right. Hopefully it's correct. So this factors as x plus 175 times x minus 100. And I'm skipping the detail there. If you would like to see more detail on how to do that, just put in the comments. I can probably just explain in a comment. That probably shouldn't be too hard. But basically, I'm using the AC method. I actually have the solution off to the side here, but 175 minus 100 is 75, right? And 175 times negative 100 is negative 17.5. So yeah, that's basically how that works. When in doubt, you can use quadratic formula to solve a quadratic equation. You don't have to do this via factoring. So I have my two factors. So either this first factor equals 0, or this second factor equals 0. So either x is negative 175 or x is 100. Okay. Now, since x represents demand for some product or commodity, you can't have a negative demand. That just doesn't make any sense, right? So x equals 100. So what I can do now is take that equation, copy it down here. So 4x, I'm going to run out of space. That's okay. 4x dx dt. This is a little more involved than previous examples. Dx dt plus 5 dx dt times p plus 5x dp dt plus 100p dp dt equals 0. I think that is everything correct. Okay, so now I can plug in numbers. 100 for x. I can plug in 2 for dp dt and 30 for p. So 100 for x. So 400 times dx dt, which again, that's the thing we're looking for. That's why we don't have a number for it. Plus 5 times 30, so 150. And I think I have a mistake here. I put a plus twice. Yeah, I just put plus twice. Okay. Plus 150 dx dt. Again, the 150 is from the 5 times p, which is 30. Okay, so now plus 500 times 2 plus 3,000 times 2 equals 0. Okay, I think that's all done correctly. So I'm going to have 550 dx dt plus, well, this is 6,000 and this is 1,000, so 7,000. So I can subtract 7,000 on both sides. So I'll have dx dt, or rather, sorry, 5,000, or 5,500. Sorry, 550 times dx dt equals negative 7,000. And then divide the 550 on both sides. Now I can do a little bit of reducing. These zeros reduced, right? And then the top and bottom are both divisible by 5. So dx dt equals negative 140 over 11. And that is approximately negative 140 divided by 11, 12.72. What was the scale of these numbers? This is quantity. Okay, we'll go with 12.72. That's fine. Or 73 rather, rounds. Negative 12.73. So this means that demand will go down by about 13 units. About, I'll say 13 units, whatever those are. Of course, if this is like some commodity that you can buy in fractional amounts, well, then we went around to 13. But we don't know the context, so we'll just go with that. So this problem was a little bit more involved than the other ones, because the last few examples, because we weren't given. We were given sufficient information. We were able to solve the problem, but we weren't given what x is up front. We had to work that out, which took a little bit more effort. So you got that. That's an example of a related rates problem.